How does it all end? This is a huge question. As human beings, we all experience many endings in life, from deaths to breakups, graduations, moves, changes. The idea of anything ending can be overwhelming. And yet, today on our show, we are zooming far out from the human experience, farther out than the end of everything we know here on Earth, and even way farther out than the death of our own sun. Today, we are talking about the end of the entire universe as we know it. We live in a dynamic universe that started in the Big Bang and has been changing ever since. That means that at some point it will reach a state where everything we know will cease to exist. No stars, no potential for life, no organized energy. But how exactly this will all unfold is a huge open problem in modern cosmology. To help guide us through this conversation today is a very exciting guest who will walk us through the 5 different ways that physicists think the universe could end. She'll also offer us some perspective on how she copes with this weighty knowledge. So stick around for this very special episode of Why This Universe.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's kind of like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee and all in the comfort of your own home or daily commute. Recently, I've been listening to a series in Wondrium entitled Understanding Russia, A Cultural History. Over 24 lectures, this course covers everything from Ivan the Terrible and Peter the Great to the role of the Russian Orthodox Church in the Revolution of 1917. It's given me some important background that really helps me understand some of the events that are going on in our world today. So if you want to learn more about Russian culture and history or just about anything else, give Wondrium a try. You can sign up for Wondrium now through our special URL to get a month of unlimited access for free. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. We have with us today, and we're really excited to have with us today, Katie Mack. She's a theoretical astrophysicist and a very well-known science communicator. She works on topics in research that include like dark matter and the evolution of the universe, and she's currently the Hawking Chair in Cosmology and Science Communication at the Perimeter Institute for Theoretical Physics. She's a huge and, in my opinion, very positive presence on science Twitter, and very recently, or more recently, she's been the author of a new book called The End of Everything, Astrophysically Speaking, which we're going to talk about today. So this book has gotten some really great reviews, Katie.
Thanks, yeah.
The New York Times called it engrossing and elegant. These are words the New York Times does not throw around lightly. I wish they reviewed my book quite as well. And I've read the book and I agree with them. I think it's really well written.
Thank you.
Thanks for putting all that effort into your communications, and thanks for coming on Why This Universe with us today.
Oh, thanks for having me. I'm excited to talk with you.
So let's just jump right in. So your book is all about the different ways that our universe might one day come to a close, come to an end. So I've just noticed something. I wonder if you agree, but among most of our colleagues, most of the cosmologists out there, this isn't something that people talk about very much.
No, yeah, it is interesting because people do talk a lot about the beginning, right? Like, I don't know, something like half of theoretical cosmology is about stuff that happened within the first second of the universe. But the coming hundreds of billions of trillions of years, there's very little discussion. I think that it's a combination of things. One is that it's untestable. Just fundamentally, you cannot run that experiment, right? We're never going to have data that can answer that question. And also, there's kind of an assumption that if we just figure out everything else, then it'll become really clear where things are going, and there's not really any practical importance to knowing that. But I mean, my perspective on it is that it is a question that is important to people. Like, people who are not physicists do want to know what's going to happen. And it's also something where just by kind of asking these questions, it puts us in a position to consider different ideas, to have, sort of creative leaps. And there are some important questions that come up when you ask yourself, how is the universe going to evolve into the future?
We're going to step through and talk about 5 different possibilities there are for how the universe will come to an end. And we'll start with what we call the Big Crunch.
So the Big Crunch was the most popular idea sort of back in the 50s and 60s. And the idea there is that, we know the universe is expanding. We know that galaxies are getting farther apart from each other. There's more space all the time, and everything seems to be moving away from everything else. And if you kind of dial that back, you get to the idea that the universe was hot and dense in the beginning. That's the Big Bang. That's what the Big Bang theory says, that the universe was hot and dense, and it's been expanding ever since. And so for a long time, there was this question of, is the universe going to keep expanding, or is the gravity of all the stuff in the universe going to be enough to put the brakes on the expansion enough that everything kind of falls back together and the universe contracts again? And the idea that the universe would contract again, that everything would go back to that hot, dense state, that's the Big Crunch.
So the Big Crunch is the idea that the gravity of all the matter in the universe will overcome the expansion of space. All of those stars and galaxies that have been expanding away from each other will slow down and start moving back together, eventually collapsing back into a state resembling the universe at the Big Bang.
So if that happened, then all the galaxies would start to come together. You'd have a bunch of galaxy mergers. That would be very exciting. But the thing that would be the really sort of fatal part of a Big Crunch would really be the compression of the radiation in the universe. So as the universe is compressing, instead of all of the light from all of the stars and the leftover light from the Big Bang and everything dispersing through the universe, it would become more concentrated, and it would also become higher frequency. It would be compressed into harder radiation.
Cosmological blue shift. That's the phrase you don't ever hear, right? Yeah, we're used to redshifting of light from the expansion of space, but the blue shifting of compression is not something we ever talk about. Yeah.
Exactly, yeah. And so, there was a great paper by Martin Rees in, I think it was 1969, working out what that would look like at the very end of a Big Crunch. And he worked out that you would get to a point where the ambient radiation of the universe would be so hot, so energetic, so much energy density in that radiation that it would trigger thermonuclear explosions on the surfaces of stars. And so you would get this kind of like runaway conflagration of all of the stars in the universe. And once that's happening, like, there is no surviving that. Right? Like, the planets are completely toast.
If that doesn't sound fun to you, don't worry too much. As far as we can tell, it's unlikely that our universe will really end in a Big Crunch.
Over time, as we did more research about a lot of things about the beginning of the universe and kind of better understood the sort of past of the universe and then better understood the expansion, it became clear that wasn't going to happen. But there was a time when it just seemed like there was enough matter that it would slow the expansion down enough that everything would collapse. That's actually the scenario that I find most disturbing, the Big Crunch. I know that it's very unlikely based on what we know now, because we know that the expansion of the universe is actually speeding up, not slowing down at the moment. But the idea that one of the things that I find terrifying about a Big Crunch is that you would totally see it coming, right? You would start to see all the galaxies blue shifting, and you would see that the ambient radiation of the universe would be heating up, and and there's nothing you can do. Like, you're just going to be slowly cooked from the outside.
But of course, it would be over such long time scales that it wouldn't affect anyone's life. That
I don't know. The idea of like we're all going to die in a fire, just.
That's all for scenario number 1, the Big Crunch. Now on to number 2, which we call heat death. Despite the name implying something with lots of heat, its meaning is more about heat as a dead form of energy. The idea is that if the universe keeps expanding, it will eventually dissipate all its energy into heat that is too spread out to form any new structures like stars.
So the heat death is the one that's kind of the most accepted as the likely end to our universe by cosmologists today. Not because it necessarily has the most evidence per se, but just because it has the most evidence given a very simple model of the universe, right? So the idea behind the heat death is that we know the universe is expanding, and also we discovered in the late 1990s that it's expanding faster and faster. It's actually speeding up in its expansion. And we also know now from other observations that the universe was slowing down in its expansion for billions of years. But something like 5 or 6 billion years ago, it started speeding up. And whatever caused that, we call it dark energy. We don't know what it is, but something that we call dark energy is making the universe expand faster. And the sort of simplest idea about dark energy is that it's a cosmological constant, which is an idea that Einstein first came up with. And it's something that is just a property of space that, the way I usually talk about it, is space just kind of has some stretchiness built in, that it just kind of like, space wants to expand. You have a certain amount of space and it wants to get bigger. There's a sort of energy in space that causes expansion. And it's a kind of weird energy. It's not something that we ever have dealt with before, but it's a property of space that it does this. And if it is a cosmological constant, then the constant part of that is the density. So the density of this expansion stuff stays the same, which means that as the universe gets bigger, there's more and more of it. And then that causes expansion to speed up more and more. And so you get this sort of runaway accelerated expansion of the universe.
To summarize, if there is this cosmological constant, then there's some inherent dark energy to any patch of space. As space expands, we get more and more space, which means we also get more and more of that inherent dark energy. More and more dark energy will accelerate the universe faster and faster.
What that means is that all the galaxies that are moving away from us now are going to keep moving away from us and move away from us faster. And although the galaxies in our nearby neighborhood, neighborhood of our galaxy, those will kind of merge with us as we're going to, our local group will become one big mush.
That's because we're bound to our neighboring galaxies by gravity that is enough to counter the acceleration of space.
But everything farther away will continue to get farther away. It'll be redshifted. The light from it will be stretched out to the redder parts of the spectrum. That'll eventually, all these other galaxies will become invisible because they're going to be moving away so quickly and so far away. So in about 100 billion years, we won't be able to see other galaxies anymore. We won't have any real evidence of the Big Bang anymore because we won't even be able to see the background light from the Big Bang, the cosmic microwave background radiation. We won't be able to see expansion of the universe. We'll just see that we are alone in the cosmos in this kind of dying super galaxy where all of the stars will sort of be slowly burning out. And because we don't have new gas falling in to form new stars, we'll be running through all our hydrogen and we'll run out of fuel to make new stars. And so all the stars we have will die. There will be more black holes from the stars and black holes coming together. Those black holes will eventually evaporate through Hawking evaporation, as far as we know. Any leftover matter will decay eventually. And so in the very, 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 very long term, you end up with a universe that's just cold, dark, and empty. And there's a little bit of stray radiation running around, and that's it. And that's called the heat death. Technically, the term heat death refers to the point where the only thing left in the universe is sort of very, very low-level thermal radiation. So just a tiny bit of the kind of waste heat of all of the universe. And so it's called the heat death because once you get to that state, you can't do anything with that energy. There's no energy gradients. There's no structure. And you've reached maximum entropy, which means maximum disorder, which means that the second law of thermodynamics, which tells you entropy increases into the future, kind of says that there is no future, right? So you sort of lose the meaning of time at that point as well, which is also kind of a weird thing to think about. And so you can have little sort of fluctuations, random fluctuations, but you can't have any progress of anything. And so that's the ultimate heat death of the universe.
All right, so we've got ourselves a big crunch option where the universe gets bigger for a while and then collapses into kind of a Big Bang in reverse. We have a heat death option where the universe just gets bigger without limit and eventually everything kind of has a slow, withering, death.
Very depressing fade away. Yeah.
I mean, yeah, none of these are optimistic. But and then
it doesn't end well.
And then we have option C or 3, what we call the Big Rip. This is maybe a little more dramatic. All right. Well, they're all pretty dramatic, but okay.
Yeah. So the Big Rip comes about if you think the dark energy is not a cosmological constant, but is a kind of exotic dark energy that we call phantom dark energy. And it's essentially, I mentioned that the cosmological constant is constant in the sense that the density of the stuff, dark energy, the cosmological constant stays constant over time. Phantom dark energy would be the density of the dark energy would increase over time. And there are lots of sort of theoretical reasons why theorists don't like the idea of phantom dark energy. It doesn't fit with some of our accepted sort of energy conditions for how the universe should work. But in terms of just looking at the data, it's very hard to rule out. So the idea is that if the dark energy is getting more powerful, if it's going up in density, then instead of just sort of moving galaxies away from each other, it would start to build up within galaxies. So there's this property of a cosmological constant where, because the density of it doesn't increase, if you have a region of space, let's say you draw a sphere around your galaxy, the amount of dark energy in that sphere is not going to go up, which means that if those stars are already sort of gravitationally bound to the galaxy, they're going to stay gravitationally bound to the galaxy. But if you have a scenario where the amount of dark energy in that sphere is increasing, then it's going to start pushing the stars away. It's going to start unraveling things that are already gravitationally bound. And so phantom dark energy would pull apart all the structures. It would pull apart clusters of galaxies. It would take planets away from solar systems, and it would build up inside objects, and it would kind of destroy smaller and smaller things over time. So first you would notice that the distant stars in the Milky Way would go away, and then you would notice that like the distant planets would go away, and then the Earth would wander away from the sun, and at some point the Earth explodes because it's just being sort of expanded from inside, and then atoms and molecules are pulled apart, and then nuclei, and it all ends with a spectacular big rip where the space itself is kind of torn asunder. And the cool thing about a big rip scenario is that if you know what kind of phantom dark energy you have, you can calculate exactly when the big rip would happen. You can work out like when that ripping point would be and how many years into the future. And so based on the current data that we have, based on sort of the uncertainties we have around what, the sort of behavior of dark energy now, we can say that at least 200 billion years we can't have a big rip within that time. So we have at least that long.
And when you talk about the time of the Big Rip, you mean where like the Milky Way as a system will start to experience it, or?
No. Specifically, technically, it means where the scale factor goes to infinity, which means that any 2 points, no matter how close they are together, are infinitely far apart. That's the Big Rip.
Now we've done the Big Crunch, we've done heat death, and we've done the Big Rip. Number 4 on our list of possible endings is an interesting one, and it's called vacuum decay.
So this is my personal favorite.
Me too.
It's also the hardest one to explain without getting into some really heavy theoretical physics stuff. But the idea behind vacuum decay is essentially that the way that physics works could change. So we have good reason to believe that in the very early universe, there was a transition that changed how physics worked. We talk about, so the Higgs boson was a particle that was discovered at the Large Hadron Collider, and the boson itself was not the important thing. The important thing was that it proved the existence of the Higgs field, which is a kind of energy field throughout all of space, and the Higgs boson is an excitation of that energy field. And the reason the Higgs field is important is because we have reason to believe that in the very early universe, the Higgs field changed, and that changed the laws of physics. So it's an energy field that's throughout all of space, and it's connected to kind of what kind of particles can exist, what their properties are, how the standard model of particle physics is put together, sort of the symmetries of the theory. That's the part that gets very complicated. But we think that in the very early universe, we had a different mix of particles. They didn't have mass. We had different forces of nature. And then the Higgs field changed. the sort of field changed its value, and then that set up the situation where we now have electromagnetic forces, the weak nuclear force, the particles that have mass, quarks and leptons, and all of that kind of stuff, right?
This dramatic change in the laws of physics that came with the Higgs field turning on is an example of something we call a cosmological phase transition. If you want to learn more about these truly mind-bending parts of cosmology, you can listen to our episode on the topic, episode number 49.
And so what we don't want is for the Higgs field to change again, right? Because we like being able to have atoms and have like particles with mass and, electromagnetic forces and all of that. So the problem is that depending on how you look at the data, our current experimental results kind of suggest that the Higgs field could change again. Not necessarily soon, but it suggests that there's a possibility that the Higgs field could undergo a shift, and the way it would happen would be through a quantum tunneling transition, essentially. So it would be a random thing that we would not be able to affect, but at some point in the universe, you could have a part of the Higgs field undergo this transition to a different value. And if that happened, then it would trigger all of the field around it to transition too. And so it would be this cascade that would create this kind of growing sphere of a different kind of space with different laws of physics, essentially. It's called a true vacuum. So in this scenario, we live in what's called a false vacuum. That bubble would be the true vacuum, where we use vacuum to mean the rules of physics, the constants in nature, all that kind of stuff. So if that happened, then you'd have this bubble of basically death kind of expanding through the universe. It would expand at about the speed of light, and everything it touched would transition into this new vacuum state where the particles can't hold together anymore. You don't have electromagnetism anymore. You don't have the laws of physics that we're used to. And then, even furthermore, it's been calculated that if that happens, then because the Higgs field is kind of at a higher value, it means that everything becomes so massive that the space inside that bubble is gravitationally unstable and collapses into a black hole. So it's really bad, right? Like, you really don't want this to happen in your universe. And based on our current understanding on the calculations we've done, it looks like it's very unlikely to happen soon, but you can work out a kind of decay time for the universe, and you get something like 10 to the power of 100 years. And that's an average decay time, right? Just like if you're if you have like a radioactive sample, it has a half-life, sort of like the half-life of the universe, which means that it could decay much sooner, right? It's a random event.
It could tip this afternoon, right? It could, yeah.
It could happen right now. It could, this bubble could have formed at Saturn half an hour ago, and it's on its way, right? Like, we don't know.
So there's always some statistical chance that our universe will just decay its Higgs field and change the laws of physics, and we won't be able to exist anymore.
Yeah, and you wouldn't see it coming because it would happen at about the speed of light. So there's no warning. That's also a good thing because it means that, like, when it hits you, you don't feel it because your nerve impulses don't travel at the speed of light.
You just become a Bolivian, right?
Yeah, you just stop existing
Right.
in a totally complete way.
Katie, you keep saying it travels at about the speed of light, but this is an important distinction, right? If it's really the speed of light, then I agree you don't see it coming. But if it has even a little delay, if it's been traveling billions of light years or something, it could build up a time delay. You could really see it coming, and that would be pretty weird.
Maybe. I don't know if it could cause any light signal to precede it. So as it's traveling through space, I think that until it affects the part of space that it's in, there's no, I don't think it creates like a wake in front of it. You know what I mean? So I think even though it might be like 0.5% less than the speed of light, I don't think you'd see it coming even then.
To be a really good science fiction story.
Yeah.
There is one actually. I mean,
what is that?
Well, so there's one called Schild's Ladder by Greg Egan. So Greg Egan writes a lot of extraordinarily nerdy science fiction. So in that story, he tweaked it so that vacuum decay would be at half the speed of light.
Okay.
So that you could see it coming, you could predict it, and that way, like, you could do something about it. If it actually goes at the speed of light, it's a terrible story because the universe ends, nobody notices,
There's
right?
nothing to say. Yeah.
Yeah, there's nothing to say.
I feel like the universe ends, nobody notices is a nice little, like, one sentence story.
Yeah.
You could just write a random, like a detective novel or something, and it just ends suddenly in the middle of the story.
That would be so upsetting. Don't do that.
Yeah.
And then there's like a postscript saying, "Oh, by the way, the reason this ended is for this sci-fi reason."
Right. Yeah. It would be very unsatisfying. So when I talk about vacuum decay, I find it a really exciting idea because you have this subtle quantum effect that destroys the entire universe. You know, it's such a cool connection between particle physics and cosmology. And it's a connection between, you know, the experiments that we're doing at places like CERN and the very, very early universe and these amazing, huge consequences. But I always feel like I need to put in a disclaimer because I do get emails from people saying that they're terrified about vacuum decay and could I please reassure them? So a couple of things. One is that, you know, the estimates we have are that it's extraordinarily unlikely to happen within the next, you know, 10 to the power of 100 years, which is a very, very long time. Also, though, I think the more important thing is that it's based on an extrapolation of the standard model of particle physics that assumes that no other physics happens, right? That there's no other theory, there's no more massive particles than what we've detected. There's, you know, the standard model of particle physics is the entire picture. And we just know that's not true, right? We know there has to be more physics out there, partially because of things like dark matter or the very early universe, like stuff that just doesn't fit into the standard model. So we don't know what that looks like, and we don't know how that'll change this picture. But taking vacuum decay to be definitely, you know, we know exactly how this is going to happen, is not really justified at this point.
Yeah, it's not worth worrying about, you know, like you wouldn't worry about a plane crashing into your house, you know, might as well not worry about vacuum decay.
Yeah. I mean, and given the fact that like there's nothing you could do about it, you wouldn't even notice, like it's just, you know. I
mean, it's more extreme than that. It's like, I don't worry about 15 different super unlikely catastrophes all happening at the same second. Like that's the sort of probabilities we're dealing with here.
Yeah.
Way more than that, even way more.
Right. Like you're in a plane crash while you're being struck by lightning and also hit by a meteor, and you're winning the lottery in 5 different states at once. All of that happening at the same time. Like it's, you know, yeah.
I can live without worrying about that. Yeah. So let's go on to the fifth and final option on this list, and that is some sort of cosmological bounce.
Yeah, so this one I kind of cheated by making one chapter about like a whole bunch of different ideas, but the fundamental idea here is that there's something that happens after the end, right? So that our universe ends and then something starts up again. There's a new universe after the end of our universe. Or in one case, there was a universe before our universe that created ours, and we don't know if there's going to be anything after. It's an idea that's been around in lots of different forms for a long time. When people first started talking about the Big Crunch, they talked about the possibility that the Big Crunch could lead to a Big Bang. It's actually not that simple. So generically, a Big Crunch does not lead to a Big Bang, which disappoints people when I tell them that, because a lot of people like the idea of a Big Crunch because it's like, oh, but then we'll have, you know, new universe. Like, no, probably not. So it's actually quite hard to get the equations to work out so that something comes after a Big Crunch. But there are models like the ekpyrotic model, which was first written down by Paul Steinhardt and Neil Turok, which is this idea that the universe has some kind of contraction, not necessarily all the way to a Big Crunch, but some kind of contraction that then leads to a new Big Bang. And then that can go over and over again. And then in some of those models, it's because there's sort of extra dimensions and there's other universes kind of crashing into our own sort of and creating a new universe. The newest version of that model doesn't have extra dimensions, but it does have some kind of slow contraction and then a Big Bang. So that's one possibility that people talk about. Then there's things like Roger Penrose's conformal cyclic cosmology, where you have a heat death followed by a Big Bang at the end of that. And a lot of these ideas are kind of driven by questions about entropy. So it's this big kind of philosophical problem in cosmology that, because the second law of thermodynamics says that entropy has to increase into the future, that kind of necessarily implies that the entropy at the beginning of the universe was pretty low, because we can calculate what it is now. And so if it's always been increasing, it had to be pretty low at the beginning, and we don't know why that should be. There's no sort of fundamental principle that tells us that the entropy should have started at the very, very low level. And so a lot of these cyclic ideas are trying to set something up so that you would you would necessarily start the universe from a low entropy state that's maybe a smaller part of a bigger universe where the entropy is more sort of spread out or something like that.
If the cosmology is cyclic, doesn't this actually make the problem worse? Like, I can always just say the initial conditions were really, really, really low entropy, and that's okay. But if I want the entropy to get big and then make it low again, that seems to violate the second law of thermodynamics. What am I missing here?
So I think that one way that you've solved that is by making the new universe come out of only a small part of the old universe. And so let's say you have the universe gets really huge, the entropy gets spread out through this huge universe, and then you take a piece of that has relatively low entropy, and then that becomes the seed for the entire new universe.
Yeah, okay.
So in these bounce scenarios, is there any chance that something from our universe could make it to the next cyclic universe, or is it a complete start fresh, everything we know is going to end and maybe a whole new universe of completely new physics emerges?
Right. Yeah, so that's a great question, and that comes to the core of why these theories are really attractive to some people, because in both the conformal cyclic cosmology and ekpyrotic case, there is a possibility of something coming through, right? You kind of have to have something coming through in order to set up the initial conditions in a sense, but in the case of the ekpyrotic model, you can have gravitational waves that kind of pass through the bounce. In the case of the conformal cyclic cosmology, you have these sort of imprints of supermassive black holes that pass through that can be sort of seen in the cosmic microwave background light. And there's very controversial papers suggesting those have already been seen. Most people would not agree that they have, but those papers exist. Some people find kind of hope in that, the idea that something will persist of our reality. Gravitational waves and supermassive black holes don't carry a lot of information. We're not going to sort of preserve the lost sea scrolls, encoding them in those. But it's an interesting idea that something could come through, and it kind of presents the sort of very extreme possibility that you could get some kind of signal or message through that transition.
Yeah, it's interesting. You can imagine a late advanced civilization trying to encode their essential knowledge into gravitational waves by moving stars around.
Yeah, exactly.
It's interesting.
That's another really good science fiction story idea. So, Katie, we've laid out the 5 options. If you were forced to say which one you think is most likely, what would you say, and by what margin? How much more likely is the most likely one, and which one is it?
I think I have to go with the heat death because it perfectly agrees with all of the data that we have, and it doesn't hypothesize anything kind of exotic. The reason I wouldn't go with vacuum decay, even though that does also agree with all the data, is that you have to make an assumption about the standard model being valid at all scales, which I just don't think is justified. That said, maybe when we figure out what's beyond the standard model, there will be some other cosmic apocalypse that will be predicted. I don't know.
So that's the most likely option, but is there one that you would, if you could choose, which one would you want to be true?
I think I'd still have to go with the heat death because it gives us the most time. I mean, I know that it's a boring idea, but nothing violently, cooks or rips us apart. So we don't want soon, and we don't want painful, right? Big rip would be painful. Big crunch would be painful, but heat death is the only one where everything kind of just chills and fades away.
So together, we've gone through the 5 ways that our universe may come to an end. Unlikely that it's a big crunch, more likely that it's a heat death, possible that it'll be a big rip or some sort of cosmological bounce. Whichever one it is, this idea that the universe is gonna one day end can be a pretty depressing one. So how does Katie Mack deal with thinking about this all the time? For a lot of, maybe especially non-physicists, thinking about the end of the universe and the end of all life or something, it's kind of, it brings anxiety for some people, maybe some existential dread. Do you ever get those feelings? Or how do you feel about the fact that the universe is going to end? Yeah, does it keep you up, or how do you feel?
I wouldn't say it keeps me up, but I went into this project as somebody who is deeply uncomfortable with the idea that I will someday die. right? Like, I do not like this thought. I'm not one of those people who's like, yeah, it's all the circle of life, whatever. Like, no, I don't want to die. I don't want my life to end. I don't want the earth to end. I certainly don't want the universe to end. Like, I'm not comfortable with that idea of, finality of non-existence. And so it was kind of a challenging thing to spend all day, every day, like thinking about the ultimate destruction of reality. That did have an impact on me. And because of that, I really wanted to get that perspective from other people I talked to. So when I went around interviewing people for the book I was mostly going around to ask about, like, the latest research in things like dark energy or what's going on at the LHC and stuff like that. But every time I had an interview with someone, I would make sure that I would ask them, how does the end of the universe make you feel? Because I really wanted to know if this was something that was, just me, or, other people whose research intersects these ideas, if they also had a sort of emotional connection to these topics. And it was a really interesting thing to see the range of answers, because a lot of, like, several people were like, I have other things to think about. I don't spend my time thinking about the end of the universe. I'm worried about climate change. And then some people said, like, yeah, this is fundamentally horrifying to me, and I'm not okay with it. And also, like, maybe it's cyclic. Maybe we'll come back. I don't know. Like, so there was that kind of, like, trying to find a way out. And then there were also people who were saying, like, yeah, actually, I think it's good that we end. I think that that's suitable and appropriate. So it was a really wide range. But for me, I think I'm still kind of working through how I feel about it. And in the book, I kind of come back to that a little bit as I go along, in the narrative, where I kind of try and look at it from these different perspectives. But it's definitely, I would still rather the universe not end. I would still rather that we just continue forever and everything's great. But I'm starting to, I think, come more to terms with it.
What helps you come to terms with it?
Well, I think that part of it is when you realize that the universe is going to end, you get to the logical step from there is that there will come a time in the future where it will not have mattered that we existed, right? Where there will be no impact on the universe from anything that ever happened on Earth with us, anything we ever did. And if that's the case, then the only way that there is any meaning to existence is if it has meaning in the moment, if it has meaning that does not connect to some future time. And I feel like that's kind of a helpful frame to think about life, to think about existence, that like we have to make our own meaning. We have to find our own way of having purpose. And when you start to do that, when you start to really kind of accept that and incorporate that into your thinking about life, I do find that kind of helpful. So, I mean, for example, when I was writing up this book, there was a death in my family, and it was somebody who I was reasonably close to, and when she passed away, I didn't have a lot of keepsakes or anything, and like, a lot of her stuff just kind of disappeared because of the various ways things happen, and I was sad about that. But then at some point I was like, well, that stuff's not going to persist anyway. Everything's going to end. Everything's going to be destroyed at some point. What matters is that when she was here, we were close. We had a connection. I had that relationship, and that's got to be what the meaning comes from. Not, whether or not I have her photo albums. Like it's got to be something that was in the moment and is in the moment and is, present. So. But I do think that there are ways that framing can be helpful. And I think that's kind of where I started coming to terms with it.
Yeah, I think it's come up on Why This Universe before, but I think I'm the only person I know who finds there to be all sorts of anxiety over the idea of existing forever. That sounds absolutely horrific to me. Just truncate it at some point, make it finite. I don't even care if it's a long time. Just make it finite, and I can live with that a lot more easily. So thanks for reminding us of the finite nature of our universe, Katie.
Yeah, sure. You're welcome.
A huge thank you to Katie Mack for coming on the show today. If you want to learn more about the end of the universe, you should pick up her book, The End of Everything, Astrophysically Speaking. Also be sure to follow her on Twitter at AstroKatie for some stellar online content. Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.